All right. So today we have Heeyeon Kim, who will tell us about 3D TFTs from 4D n=2 BPS particles. Take it away.
Thank you. I'd like to thanks to Julius for inviting me to this nice seminar series. So today I'm going to talk about some algebraic structures that arises from some interesting class of 3D topological field theories that can be obtained from 4D n=2 SCFTs, in particular the data of their BPS spectrum in some precise sense that I'm going to explain as I move on. So the structure of vertex operator algebras in 3D supersymmetric field theories has been extensively studied in the last 10 or years. So the setup is the following. So in the Burke 3D, you have you define your Burke 3D supersymmetric field theory probably on some 3D half space, say the C times R minus. And to have some control over it, you perform certain twists. For example, in 3D n=2 theory, you can perform the holomorphic topological twist. And in n=4 theory, in addition to it, you can also perform the topological A twist, the topological B twist to pass to the fully topological field theory in 3D. And depending on the twists, there are some set of boundary conditions that you can be imposed on the 2D boundary so that it's compatible with the topological twist that you have chosen in the Burke. And on the 2D boundary, there are interesting algebra of local operators, which often form the structure of the vertex operator algebras. So the most well understood examples of those 2D vertex operator algebras are rational vertex operator algebras. This is nothing but that describes the chiral parts of the rational conformal field theories. And this rational conformal field theories is something that characterized by the fact that its Hilbert space decomposes into a finite sum like this, where R and R dot R bar are some finite indices. And accordingly, the correlation functions that are defined on a Riemann surface also decomposes into a sum of this finite sum of a product of holomorphic and anti-holomorphic functions. And examples of those rational vertex operator algebras include Virasoro mineral models or the affine Lie algebras, the integer levels, etc. However, most of the vertex operator algebras that arise from the 3D supersymmetric field theories that I illustrated in the last slide have some exotic features, and in particular, they are not rational. The reason that this is true is that it's because there exists some local operators, some non-trivial local operators in the Burke twisted theory. So for example, in this picture, if you consider the 3D n=4 theory, where you can obtain 3D fully topological twisted theory, after the A twist, the Coulomb branch operators of the original n=4 theory remains as a local operators in 3D Burke theory, and that's one of the reasons why the vertex operator algebra induced in the boundary is not rational and has some more exotic features. So let's consider some 3D n=4 supersymmetric superconformal field theories. There are two important necessary conditions for this theory to admit rational vertex operator algebras in the boundary. The first condition is the Coulomb branch has to be zero-dimensional, so that there's no local operators, for example, in the A twisted theory. And also the second important necessary condition is that Higgs branch is also zero-dimensional. And these two, the SCFT that satisfies these two conditions are called rank 0 supersymmetric conformal field theories. The problem is that it's difficult to construct such a rank 0 SCFTs because it conjectures that there's no interacting Lagrangian rank 0 superconformal field theories. But there exists in literature some examples of non-Lagrangian rank 0 SCFTs. The first example appears in this paper by Kang and Yamazaki in 2018. It has a simple, very simple ultraviolet n equals to 2 Lagrangian description. It's given by this very simple Lagrangian. It has a U1 gauge group with a Chern-Simons level 3 half. And there is a chiral multiplet which is charged under this U1 gauge group. And if the theory flows to an IR fixed point, it's expected that it has a accidental supersymmetry enhancement to the n equals to 4, the fixed point, and that supersymmetry conformability theory is called T minimum. So the reason that this is called T minimum is that in many sense, this can be thought of as a minimal n equals to 4 SCFT. Just like for the n equals to 2 simplest Argyros-Douglas theory, for example, it has the minimal central charge among the all known examples of 3D n equals to 4 SCFTs. And this is now, the infrared theory is now an n equals to 4 theory. So the theory can be topologically twisted to produce 2 different topological field theory under the topological A twist and B twist. And the supports that are expected to support some interesting rational vertex operator algebra. In this case, it turns out to be the Virasoro minimum model M2,5. Which is the simplest example of the non-unitary Virasoro minimum model, which is sometimes called the Liang singularity, or its parity conjugate, depending on the topological twist that you choose. Okay. But in general, it's going to be not easy to systematically generate such an example because such an IR supersymmetry enhancement is in general difficult to predict from the UV gauge theory. With some of my collaborators, I have been recently developing somewhat more systematic ways to construct those large class of rank 0 theories. And this program is based on a simple observation that a large class of characters of rational vertex operator algebra, which turns out to be a modular function, is a modular function of weight 0 under some congruent subgroup of SL2Z, takes the following formula. So it's many of the rational vertex operator algebra takes one of these form for some choice of R by R matrix, say K, and some R dimensional vector B, and some rational number C. And this formula is called the NUM-SUM formula. And here are some simple examples. The characters of the Virasoro minimum model M2,5 that I mentioned before can be written in this simple form. And this identity is called the Rogers-Ramanujan identity. And interestingly, also the critical Ising model, an M3,4, also takes this form, where this R by R matrix K is nothing but this 2 times the Cartan matrix, the inverse of the Cartan matrix of the EA algebra. So there are some interesting the formula that relates this form of the NUM-SUM and the rational vertex operator algebra, or more general class of the vertex operator algebra. And our starting point is that at the same time, the formula that I showed here is also the formula for the half index of an n equals to abelian Chern-Simons matter theories of the following type, where we have the gauge group U1 to the R with the Chern-Simons, mixed Chern-Simons matrix K, where this K matrix is the same as this matrix K that appears in this NUM-SUM formula. And we also have the R chiral multiplets. And each of the U1 factors exactly have 1 chiral multiplet charged under it. And this half index of this theory can be computed, and if this is computed with some specific choice of the boundary conditions, and you can show that it reduces to one of those formulas. Also, if the boundary condition is compatible with the topological twist that we perform on a Berg, this half index can be identified with the character of the boundary of VOA. Then from the relation that I mentioned between the rational vertex operator algebras and the n equals to 4, 3D n equals to 4 rank 0 theories, it's natural to conjecture that this provides some sort of the generalization of the simplest, the n equals to gauge theory description, the UV gauge theory description that I showed you in the beginning, so that it's kind of something that provides an n equals to gauge theory description that flows to n equals to 4 rank 0 SCFT in DIR, possibly after some superpotential deformations. Okay. And this proposal can be checked indirectly via many different computations of various protected quantities. Here are some simple examples. The simplest example is given by the following. So you consider this 3D n equals to 2 theory, you want the R, the gauge group, where the tensile mass level K, the matrix K, is now given by the Cartan matrix of what's called the Tedford diagram. The Tedford diagram is, I think it's actually the inverse of the Tedford diagram. It's a typo. The Tedford diagram is nothing but something that you can obtain by defolding the A to R Cartan matrix in half. So A to R diagram in half. So it's basically the same as the Cartan matrix of AR, but the very last entry in that matrix, which is 2, is replaced by 1. You can check that this theory has just the right number of top BPS monopole operators. So you can add to this potential to completely leave the Coulomb branch. There are exactly R-1 monopole operators, so that the U1 to the R topological symmetry completely breaks down to the U1 symmetry, which becomes a part of the R symmetry in the IR n equals to 4 SCFT. And then you can compute various protected quantities, and the results suggest that the theory indeed flows to a class of rank 0 n equals to 4 SCFTs with enhanced supersymmetry as expected. Okay. And depending on a twist, either A or B twist, you can also argue that this theory, if you properly choose your boundary condition, it supports the boundary algebra. For example, in the case of A twist, there's strong evidence that it supports the Virasoro minimum model 2, 2R plus 3. In the case of B twist, it supports the simple affine OSP1/2 algebra level R. And relatedly, in a work by Zagier in early 2000, there was an attempt to classify all modular NUMSUM formulas. And this attempt was by using the NUMS conjecture relating the modular functions, and it's called the torsion elements in block group. Okay. The complete answer is still an open problem, but in this paper, Zagier found a large class of examples can be candidates of RCFT characters. So in this paper, he almost fully classified the example of those NUMSUM formula here. For example, they found K, the matrix K, that admits B and C, so that this full character chi is a modular function under some congruent subgroup of SL2Z. And that was for example, in that paper, that is performed for the R equals to 1, 2, 3. And as a result, they obtain like 20-something examples, depending on how you count it, with some other infinite families of examples. And an interesting test of this rank 0 conjecture, the relation between the rank 0 theories and the rational vertex operator algebra that is supported on the boundary of the twisted rank 0 theories. It's natural question whether if you can perform a complete scan over the space of n equals to a billion tensile mass matter theories with R chiral multiplets, so that at half index give rise to precisely the norm sum type formula that I showed you in the previous slide. Can be indeed the candidate description for the UV gauge theory that flows to the 3D n equals to flow rank 0 SCFTs. And we have checked that this in fact reproduces, and in physical picture, in fact, it's slightly generalized the result of the Jaeger in Newton. Okay. Any questions so far?
So far, so good.
Question. I have a question actually.
Mm-hmm.
What examples do you get that are beyond the Jaeger classification? And do you know what vertex algebras they might correspond to?
Yeah, the vertex algebras corresponds to we don't find anything more than like a usual Virasoro minimal models, and some W algebra examples. Yeah, and some the level rank dual to the Virasoro minimal model examples. Those are pretty much the everything that we find. There are many different matrices of matrices that K that makes this pi the modular function, but many of them falls into the same duality class, and it turns out that there are only like 8 or 9 different duality class that we obtain, and these are all like a known types. So in Jaeger's paper, they don't explicitly describe precisely which vertex operator algebra that this modular function corresponds to. So yeah. And some other we found some other matrices that didn't appear in his classification, but this vertex operator algebra is not something new.
Okay, great, thanks.
Any other questions? All right. So that was the review of recent the result. But the main question for this talk is the following. So the observation, another interesting observation is that many of these rational vertex operator algebras that I described just now are the one that also appears in the context of the 4D n equals to SCFTs. So in this work by Bim and mostly in the Pilares-Lastellian families, there was they constructed a precise map from a given 4D n equals to SCFT to some 2D vertex operator algebras. So for example, this map gives, if you start from the Algebras-Douglas theories of type A1, A2R, this map gives precisely the Virasoro minimal, the M2, 2R plus 3, the one that we encountered in one of my previous slides. Okay. So the question is, what's the precise relation between these two constructions, the one that constructed from the 3D n equals to 4 rank 0 theories and the one that appears from the 4D n equals to SCFTs? Before I discuss some underlying physics, let me briefly review some relevant previous works and point out another interesting observation about this. So the operator that participates in this 2D vertex operator algebras comes from the so-called Schur operators in 4D n equals to SCFT. These are a class of operators that passes the cohomology with respect to certain combination of the supercharges in 4D n equals to superconformal field theory. And then the Schur index of this 4D n equals to superconformal field theory, it calculates the vacuum character of the corresponding 2D vertex operator algebra, which is defined by this. And one of the remarkable formula that allows us to calculate this Schur index is given by this paper by Cordova and Shao in 2015, and also related work is in the much earlier by Chekuti, Naitsky, and Baba. Remarkably, what is argued in this paper is that the Schur index can be calculated in the infrared theory with the data of the Coulomb branch BPS particles. So to illustrate how this comes about, for a given BPS particles, and 4D BPS particles in the Coulomb branch with electromagnetic charge gamma in some lattice, we can assign some quantum torus algebra variable big X gamma, where this X gamma is defined by the property that it satisfies this commutation relation. And if you look at a chamber of this Coulomb branch that contains n BPS particles, say, then you can calculate the Schur index using this remarkable formula given by the trace over this quantum torus algebra, where inside this trace, you have a product of Q exponentials. This function E sub Q is a Q exponential which can also be defined as a 1 over some Q per gamma symbols. And its argument is precisely this quantum torus algebra. And the order of this product has to be chosen in a specific way according to the phase of the central charge of each of the BPS particles. And as you can imagine, this IR formula depends on the choice of a particular Coulomb vacuum, which is defined by this complex number U, for example, in the SU2 case, rank 1 case. But you can also argue that the final result, the trace formula, does not depend on the specific choice of Coulomb vacuum. In particular, this the Schur index, you can show that this is Y-crossing invariant. This is due to the identity, this famous pentagon identity that Q exponential satisfies when the gamma and gamma prime has this relation. Okay, this is in general says that this formula is invariant under the various Y-crossing movement. And an interesting observation is that after you perform this trace, after you evaluate this trace, the final expression also naturally takes some formula, but it's slightly different from the standard sum formula that I showed you in the beginning of the talk. But anyway, this can also be interpreted in various different ways as a half index of 3D abelian transassignment matter theories. So here's an example. If you start from, say, the simplest Argyros-Douglas theory, that has two BPS particles, the electric particle gamma 1 and magnetic particle gamma 2, which has an intersection 1. And if you apply your the master IR formula to this theory, it gives rise to this particular sum expression there. And you can immediately identify this Schur index, this formula of the Schur index, as a Dirichlet half index of a 3D n equals to 2 gauge theory. And this gauge theory has the U1 times U1, and this transassignment matrix K is given by a simple transassignment level A1, D, A2 type, where A1 and A2 are the connections for each of the U1. And there are 4 chiral multiplets, and for each of U1, the gauge group, it has exactly 2 chiral multiplets each that are charged 1 under this U1 gauge group. We are going to discuss the physical derivation of this abelian transassignment matter theory at the end of the talk. But for now, I'm going to just explain the observation that this theory that I illustrated here is related to the original description of 3D rank 0 theory, the T minimum theory that I explained in the very beginning of the talk, by applying a chain of elementary 3D dualities. Which, for example, this is a description that I just showed you in the previous slide, this one here, where as usual, the circle node is the U1 gauge node, and this square node is a U1 flavor node, and these lines are just one chiral multiplet, and this dashed line represent the mixed transassignment level, and this number is just mixed transassignment level between these two gauge groups. So this is the description, this U1 to the 2 description, and you perform a particle vortex duality for this chiral multiplet that gives rise to this quiver. And then you perform another the run of the particle vortex duality on, say, this chiral multiplet that gives rise to this particular quiver. And finally, you can also perform SQED XYZ duality to arrive at the original description, original UV description of the T minima theory, which is the first example of the n equals 2 theory, which is known to flow to the 3D n equals 4 rank 0 theories. And each of those theories contains some superpotential coupling so that each step is consistent with the theory. And you can also trace this duality chain at the level of the half index. For example, these four expressions are the four expressions that correspond to each of the quiver there. And you can in fact show that they are all equivalent description. And in fact, the last one coincides with the well-known lump sum expression for the M2,5, which is the Liang model example.
Can I ask you about the nom-sum formula that you had 2 slides ago? The one before this one even, or yeah, this one. So why do you sum over the flavor charges rather than the full charge lattice? Or where does this constraint that it lies in the flavor charge sublattice come in?
So if the flavor is trivial, just like in this example, this implies some particular constraint among the set of charge vectors you sum over. So for example, if it turns out that the gamma f is trivial, just like in this Douglas theory examples, then this in fact just implies that this constraint just implies that the gamma 1 is equal to the minus of gamma n plus 1. So here I also include the particle and anti-particle. So it in fact just simply become the ordinary sum over just over the positively charged BPS particles.
Oh, okay, cool, great, thanks.
Any other questions? And with the exact same data of BPS particles, you can also define many different the word crossing invariant quantity with a similar structure. And one of the examples is given by the considering the so-called fermionic versions of quantum dilogarithm. Okay, so instead of this Q exponential that we defined before, you can use this inverse. Essentially, this is inverse, which is sometimes called the fermionic quantum dilogarithm. And this product is the order of this product is in the opposite of what we had before, so that the various word crossing movement of this expression is well defined. You can show that this is another word crossing invariant. In the fermionic version, in fact, it has much better convergence property compared to the bosonic one. And typically, out of this fermionic index or invariant, you can get much simpler 3D descriptions that give rise to some topological field theory that bounds interesting vertex operator algebra. And in fact, this version of invariant and its various different generalizations was extensively studied in this paper by Chakoti, Song, Vafa, and Yang in 2015. And you can show that this particular formula also produces a character of another rational VOA, which is in general different from the one that you directly obtain from the 4D n equals to SCFT. But those two actually the one that falls into this generalized class has the same fusion rule, but it turns out to be the different the vertex operator algebra. But it has the 4D interpretation of this fermionic trace formula is not very clear, but if you go down to the 3D gauge theory, it has a very clear physical meaning. And you can show that this fermionic trace formula can be identified with the half index of the parity reverse 3D gauge theory that takes the Chern-Simons level k to minus k. And you can perform various word crossing manipulations which were unsafe with this photonic one because of this convergence issues. For example, if you start from the A1, A2, Aldrich-Douglas theory, the trace formula, the fermionic version of the trace formula gives rise to this one. And you can perform the word crossing movement, for example, for these two expressions that give rise to these three different expressions. And then you can also use these identities that these two gives you Jacobi theta functions, and you arrive at this formula. And the evaluating trace is straightforward with this example. You see that this can be immediately identified with this expression. You can probably see that this is a specialized version of the rational vertex operator algebra that we discussed before, which appears as a parity conjugate of the M2,5 minimum model. It's an simple affine OSB1/2 at level 1. It's a level dual pair, or at the same time, this happens to be also mirror dual of this M2,5 minimum model that I explained before. And motivated by those examples, we can, in fact, write down a very universal formula that computes the ellipsoid partition function S3b that computes this ellipsoid partition function for the 3D n equals to 4, some 3D n equals to 4 rank 0 theory from this 4D BPS data. So it's given by this expression, where now the inside the product, this function phi of b is nothing but the Faddeev quantum logarithm. And this acts naturally on some auxiliary Hilbert space. And these variables, it's the argument of the Faddeev quantum logarithm now satisfy the Weyl algebra given by this, where we again assign this variable for each of the BPS particle gamma for the 4D n equals to 2 Coulomb bridge. And again, this trace is also word crossing invariant. This is because of another pentagon identity that this Faddeev logarithm satisfies. Like this. Okay. So we can again consider this A1, A2, the simplest Aldrich-Douglas theory. And our proposal for the three-sphere partition function can be written in this simple way. And you can perform a simple word crossing movement for these two the phis to produce the product of three phis. And you can use this another identity, nice identity of the Faddeev logarithm that annihilates these two and annihilate these two to arrive at this expression. And you take a trace over that Hilbert space that I mentioned, we immediately recover this formula, which is nothing but the standard formula for the partition function of this, the simplest, the UV gauge theory descriptions that flows to the n equals to 4, the rank theory that's called P minima theory. So you can do the similar game for many different supersymmetric observables in 3D n equals 4 rank 0 theory. In particular, you can also write down a similar proposal for the 3D superconformal index. It turns out to be 1 in this particular twist that give rise to the formula that counts the Coulomb branch operators in 3D n equals 4 rank 0 theories. Is there any questions so far? So now let me move on to what are the precise physical fixture that underlies all these observations that I just mentioned. So what are the relations between those 3D n equals 4 rank 0 theory whose various partition functions are given by those trace formula and the original 4D n equals to SCFTs. So the twist that give rise to this picture of the vertex operator, 2D vertex operator algebras in 4D n equals to SCFT is this picture of the holomorphic topological twist. So you consider 4D theory on R2 times C, where on R2 you perform topological twist and over C perform a holomorphic twist. And you consider the omega deformation on this plane to turn it into a cigar like picture. And then you can show that the algebra of the local operators in the holomorphic topological twisted theory, in fact, localizes at the tip of the cigar like this. And we obtain a 3D n equals to 4, some 3D n equals to 4 supercompactification theory by performing a circle compactification along this circle, the cigar circle. And the resulting picture is you have a 3D theory on the defined half space, for example, with the two boundaries, one at the tip of the cigar and the other at the infinite boundary. And then the remaining direction is the C, which is a 308. This construction has been recently also discussed in this recent nice papers too. And what's important is that this process involves the topological twisting by the U1 R symmetry in the 4D equals to superconformal algebra. So in the topological twist of this R2 plane, you have to turn on some background flux for this U1 R symmetry. And this induces, as you compactify this circle, you also introduce another 2 pi rotation of this U1 R symmetry. This is U1 small r symmetry. So as you go around this circle, it also induces the 2 pi rotation of the U1 R symmetry according to this relation. Of course, this is a 2 pi rotation, so it turns out to be a trivial action for the Lagrangian theory, but all the charges part, all the spectrum has the integer U1 R charges. But in general, for non-Lagrangian theories, such as Aldrich-Douglas theories, this operation gives rise to some non-trivial result because some of those spectrum contain fractional U1 R charges, and this the extra twist results in something very non-trivial. So the result of this twisted compactification can be understood most easily in the point of view of the 4D Coulomb branch. And each of the point in the Coulomb branch is described by some abelian gauge series. So this is the usual U-plane picture. And as we know very well, the properties of each vacuum in this Coulomb branch is described by a collection of central charges Z gamma of U. And these BPS particles are defined by the property that it satisfies this relation. And we are going to just focus on a chamber that contains a finitely many heaven multiplets on it. So to explain this, the relation to twisted compactification, let's consider the following situation. So we have an effective the coupling constant tau of the 4D effective abelian gauge series. And we consider this coupling constant tau varies as we move along the x3 direction, where this x3 direction is something that the direction that we are going to compactify on to go down to the 3D. And such a choice of some configuration of tau as a function of x3 is going to be described by a path in the U plane. Okay, so this tau is a function of U. So the tau of x3 is going to give rise to a certain path in the U planes. For example, in this rank 1 theory, it's gonna be some it's a line inside of this complex plane. So in general, the generic such a choice of tau of x3 is going to break the supersymmetry, but you can preserve the n equals to 3D n equals to sub algebra in the remaining direction if it satisfies the following condition. So the central charge of the effective theory that are defined on this 3 direction is given by the rear of this 4D central charge. And if this quantity stays constant along this path, you can project 3D n equals to 2 algebra along this path. Okay. And suppose that you have a 4D BPS particle gamma that satisfies this condition. And in order for this particle to saturate the 3D BPS bound as well, which is this relation, m is equal to the real of z, we need this relation. This implies that this relation implies that the imaginary part of the central charge has to vanish. For example, suppose that this red line is a line where the real of the central charge is constant so that it preserves some 3D n=2 subalgebra. And the point where this is satisfied is going to be generically some codimension 1 point on this curve. Okay, then this means that there exists a certain number of points on this line where this 4D BPS particle gamma become also a 3D BPS particles. And we say that these 3D BPS particles that comes from the 4D BPS particles are trapped at these loci. Okay. And each of these particles are going to behave as a 3D chiral multiplet with the same charge plus minus gamma that is inherited from the 4D n=2 BPS particle charge. So to summarize, from that the Janus slide picture, what we obtain is the 4D abelian gauge theory coupled to various 3D chiral multiplets as we move along the x3 direction. So that was the path that I draw in the previous slide. And there are a certain number of points where you can also find 3D chiral multiplets. And these chiral multiplets in general have electric charges and magnetic charges at the same time, so that all of these particles cannot be simultaneously included in a standard electrically charged, as a standard electrically charged particle in some effective U1 gauge system. So what we must do is to every time we go from some electrical charged particle to say magnetically charged particle, we have to insert some duality domain words between those particles, so that in each neighborhood, these particles just become a standard electrically charged particle in its own local duality frame, and then we just move them by inserting some duality domain words. So these are just abelian gauge theories. And in this case, such an S duality domain was can be simply understood as just adding the mixed transimals level like ADB, where if A is a local gauge field around this chiral multiplet, and B is a local gauge field around the chiral multiplet, and if this is an electric and if this magnetic, and the duality domain was can just be described in terms of this mixed transimals level. And if you summarize everything, the resulting 3D gauge theory is in general in a form of some n=2 abelian gauge theory with some complicated mixed transimals levels and various chiral multiplets. And there are some non-perturbative effects, which is going to, in general, generate very complicated superpotential interactions among various fields in this gauge theory. This construction has been called the R flow. It has been studied, for example, in Chekhotin in 2010, or also in Chekhotin called Vapa in 2013 work. Okay. And the situation that we are interested in is slightly different. We want to consider we want to replace essentially the line, the x3 line, and we replace it by a circle so that we can compactify on the circle. And the U1R twisting along the circle that corresponds to performing the extra 2π rotation of the U1R symmetry, it corresponds to the situation where the central charge uniformly rotates because of this 2π U1R twisting, uniformly rotates its face along the circle like this. So as you go around, this path, you expect that the set of central charge that corresponds to the BPS, that of BPS particles, also the uniformly rotates. Its base uniformly rotates so that you make a full 2π phase around this circle. So in general, such a path, if you draw any path like that, not going to preserve any 3D n equals to sub algebra, but you can deform it to one that preserves the 3D n equals to algebra by massaging this curve. But since all the property quantities that we are interested in, the one that I showed you before, for example, those trace formulas for the Schur indices and trace formulas for the three-sphere partition function, they all turns out to be the workhorse invariant. So this formula that we obtain is going to be invariant under such a movement. So I will end by explaining how this comes about for the simplest example. So we consider, again, the simplest Address-Douglas theories, A1, A2 theory, that has this simple Quiver description, where the gamma 1 is electric and gamma 2 is magnetic. And this is a compactification circuit that I mentioned. We have 4 locations on this curve where the BPS particles are trapped. There's a gamma 1 and gamma 2. There's minus gamma 1, minus gamma 2. Because this is electric, it's magnetic, you have to introduce some S duality war, and you also have to introduce another S duality war here and here too. Okay. And this particular configuration, if you compactify this on this circle, this configuration gives precisely U1 to the 4 gauge theory. Each of the U1 corresponds to local gauge field around those 4 BPS trapped particles, and there are also 4 chiral multipliers that comes from these 4 locations. And you also have to include these 4 S duality words that give rise to this particular Chern-Simons coupling. And it turns out that this description is precisely the one of the UV description of the T minimum that we introduced in one of the previous slides. So that's pretty much it. So the outlook. So first of all, to summarize, the twisted compactification of those 40 SCFTs, I was trying to illustrate that this can be understood in the Coulomb branch effective theory. In the dynamics of BPS particles are included in the Janus-like configuration along this compactification circle. This gives a 3D n equals to the abelian Chern-Simons meta theory description that can be thought of as some UV description whose IR fixed point showed some sort of supersymmetry enhancement. So these 3D theories are expected to exhibit supersymmetry enhancement in the IR, and for non-Lagrangian theories, they often produce 3D n equals to rank 0 SCFT if the R charges of those 40 SCFT meets certain conditions. It's gonna support some rational vertex operator algebras on the 2D boundary. And then by a duality chain, you can recover a very simple abelian Chern-Simons meta description of the rank 0 theories that I mentioned. And also this framework produces a huge class of n equals 2 Lagrangian theories, which have supersymmetry enhancement in the IR, and then they can be used to predict new level rank dualities as we illustrated recently. Okay, that's all I wanted to say today. Thanks.
All right, let's thank Heeyeon. Do we have questions? So I have one. Can you do similar things for not rank 0 theories? Like,
yes, yeah.
Find some interesting like rank R theories in 3D that like we don't study because they're like as exotic as the rank 0 ones, that they come from some 3D to Lagrangian and something like this.
Right. Right. In fact, this for example, if you consider the 40n equals to SCFT that contains non-trivial Higgs branch and Coulomb branch at the same time. For example, if you think about the simplest example would be the A1, A odd type Douglas theories. When you compactify, when you twisted compactify this down to the 3D theory, it's gonna give you the theory that has either Coulomb branch or Higgs branch. In general, it's going to produce some algebra that's not rational. So as an example, if you consider like a simplest example, the A1, A3 theory, the resulting algebra is going to, resulting 3D topological field theory is something that is going to support the affine SU2 at some fractional level.
And do you know how the moduli spaces compare if you have a moduli space in 3D, like how it comes from the 4D moduli space?
Yeah.
Like, would the Higgs branch be the same, or is there some quotient, or is it a reduction? Or?
Right. I think the Higgs branch is the same, but the Coulomb branch can change drastically depending on the R charges of the original ODM equals to BPS. Yeah.
Okay, thank you.
Can I ask one question?
So
how crucial in your say in your story of getting the 3D theory from the from the effective action of the 4D theory, so how crucial is superconformal symmetry? So you can start with a BPS particle spectrum of non-conformal theories, right? So what goes wrong if you do without conformal symmetry?
This U1R compactification is going to be anomalous. Then you need the U1R in order to perform this twisted compactification.
Can you do with some discrete subgroup of that? Discrete part will be there.
Oh, I see. Yeah, that I haven't thought about it. Yeah, it's something to think about. Yeah.
Can I ask about sorry.
Sorry, you can go ahead.
Thanks. About the non-vacuum characters, so on the VOS side, does it take a similar form? And on the supersymmetric side, I guess in principle, in the 3D equal to theory, you can just insert Wilson lines, and that should give you non-vacuum characters.
Not in general. There are some cases where the Wilson line give rise to some simple lines in the IR TFTs, but in general situation, you have to consider some other disorder operators like vortex operators or something like that.
Thanks.
I was curious about whether you have any control over the superpotentials in doing this twisted compactification.
Yeah.
You said that there were some hard non-perturbative effects that you have to take into account. Do you have any hope of recovering what the thing should be in 3D?
Yeah, it would be great if we can in fact recover all the information about the superpotential deformations, but I don't know what is a systematic procedure for that. In this work, I just write down the 3D candidate gauge theories, and there are some class of dressed monopole operators that you could add to your superpotentials, and usually they are very restricted. And then among them, you choose the set of monopole operators so that it breaks all the Coulomb branch symmetries, and that usually, in many cases, almost uniquely determine what superpotential you are gonna get at the end of this complicated procedure. It would be, in fact, nice to derive this from more first principle, story from the 4D n equals 2 setup.
So in these examples where you were doing various particle vortex dualities and XYZ SQCD duality, presumably you knew you had an XYZ at some point, so an XYZ superpotential.
Right.
was there was it the situation where you knew you had SQCD and you knew after you applied the duality transformation you'd get XYZ, or was it the other way around where you sort of knew you had an XYZ type superpotential and you could reduce it to the gauge theory?
Yeah, no, we didn't have an information of the superpotential in this analysis. It's just we can perform those chain of duality at the level of like a supersymmetric observables that doesn't know anything about the superpotential informations. So we assume that there must exist some sort of superpotential in the beginning that makes all this duality works. Was that the question?
Yeah, that was pretty much the question. Thanks.
Do we have more questions? If not, then let's thank Heeyeon again. And we can go off the record.